We have elementary operations. Either we call them elementary row operations or elementary column operations. We transform a matrix into another matrix, and the properties of that matrix remain same. First operation is interchange of any two rows or two columns. Symbolically, the inter I and j. Okay, this is denoted not open. We can interchange any two rows or columns. Let's say we have ith row and jth. B2, B3, C1, C. How many rows? This is row 1, row 2, row 3. Let's consider we are changing R1 with R, R1 with R3. So R3 will become R1 and R1 will become R3. So we will get C, B1, B2, B3, and here instead of R3 we will place here R1. So A1, A2, A3, and we will write it as R1 goes to R3 and R3 goes to R2. Both sides simple implication. Second, second is multiplication to the elements of any row or column. Let's consider a matrix A. Matrix A 1 2 1 1 1 2 2 3 8. Let's consider this matrix. We have row 1, row 2, row 3. We can multiply any non-zero real number to one of the rows, or maybe sometimes two rows, sometimes all rows you can. That we will also treat as elementary operation, multiplication to the elements of any row or column by a non-zero number. So let's consider this first row 1. Let's multiply it with 2. So R1 gives twice R2. R1 2 times R1. So instead of R1, its elements will get 2 times. Here it was 1, So this matrix will get converted into 2 into 1, 2, 2 into 2, 4, 2 into 1, 2. Rest of the elements will remain same, 2, 3, 8. So we will write here multiplication to the elements of any row or
Sir, sir, sir.
column. Yes, by a non-zero. If we multiply it by 0, then all the elements will become 0. So we will not get the same matrix. That will be later when we will be dealing with rank, eigenvalues, and finding inverse. This will be helpful. If we multiply with 0, this whole row will become 0. Then our matrix will become singular. We need non-singular matrix in that case. For finding inverse of matrix, we need non-singular. If we multiply with 0, that row or that column will become 0 and our determinant
Sir,
will become also 0. Yes. Tell me. After 6.
C chart. Sir, C chart.
Ah, Tell me, Toyajaksh, what's your concern? After 6 p.m., you
C
should
chart, sir.
say good evening and greeting someone, as it is appropriate phrase for the period from the late good afternoon until nightfall. Okay, usually I choose. I have also learned from someone. They usually say after 3 we say good evening. Afternoon is little bit only when you do lunch, like 12 to 2 usually. Symbolically, the multiplication of each element of the ith row by k. Let's say we are multiplying with k, where k is obviously not equal to 0, is denoted by ri, rho I goes to k times r. Ith row will become k times ri. The same transformation on a column is denoted by ci goes to k times. This k is some scalar, that means non-zero constant, any real number which is not equal to 0. Third is combination of first and subtraction of elements of one row to form the corresponding elements of the other row. Addition or subtraction. Okay, I will write this in bracket. So either you do addition of elements of one row So when we are doing subtraction, then we subtract from, right? Subtract from the corresponding elements of the other. Take, let's say this is our matrix B, 2 1 2 3 2 2 7 1 8. This is our matrix B. We can subtract the elements of any row from any to any column, any row to any other row. Let's say this is row 3, this is row 2, this is row 1. This is column 1, column 2, column 3. Take row first, subtract it from row 2. So what we will write? Row 2 gives row 2 minus row 1. Okay. So what will be our matrix B become? 2 1 2. We are subtracting row 1 from row 2. So 3 minus 2, 1, 2 minus 1, 1, 2 minus 2, 0. And this will be remain unchanged, 7 1. And we will write it like this. And symbolically, how will we write? Symbolically, the addition and subtraction of the elements of ith row. Here I will write same from. Shall I erase this B matrix here? That I will write here from corresponding elements of jth row denoted by Ri goes to Ri plus minus margin. Similarly, if we are subtracting or adding column, then we can write column transformation denoted by Ci goes to Ci plus minus Cj. Here we are adding Cj, elements of Cj to the corresponding elements of Ci. Let's say here we have, okay, I will give an example in next page. Take this matrix G12, 412, 7, C1, C2, C3. What we will do? We will add first column and second column and keep it at first column. Okay. So C1 gives C1 plus C2. Then our matrix will become 3 plus 1 corresponding elements we will add 4, 4 plus 1 5, 7 plus 2 9, and remaining columns will remain unchanged. 1 1 2 2 2 2 will become our new matrix. Now we have equivalent matrix. Two matrices are said to be equivalent if their order must be same. Otherwise we can say two matrices A and B of same order are called equivalent matrices if one of the matrices is obtained by the elementary row or column transformation from first we have matrix A. We either we apply row transformations on it and it will give us some other matrix. Here we operated column transformation, we got this matrix. Let's consider this as matrix B. Now these two matrices are equivalent. Equivalent matrices. I will write the definition here. They are not equal, they are equivalent. Equal means everything is same. Their corresponding elements are same. But equivalent here, if you see, first even first entry is not same, but they are equivalent. We have done column transformation here. So these are this matrix B. We got it from matrix A by doing elementary column transformation. Two matrices A and B of same order are called equivalent matrices if one of the matrices obtained by the elementary row or column transformations. A and B Okay, now we have two matrices A and B are called row equivalent if one of the matrices either A or B is obtained by the series of elementary row transformations. Here in previous slide we got A A from we did some column transformation, then these matrices A and B are here column equivalent matrices. Now why we are doing this? Because we have matrix equation. To solve those matrix equation we do this, and we can easily solve some questions based on these. Like if we want to find inverse of a matrix, this is also procedure to do. Like we already know A B, if this is equal to in, then we If we know one of the matrix, we can easily find the matrix B. The only thing is our matrix A must be non-singular. Our matrix must be non-singular.
Teacher,
I have one more student today. Elementary transformation to matrix equation. Now what we will take? We will take a matrix X and we will take matrix A and matrix B. Matrix A will be our square matrix, matrix B will be our square matrix, and X will be our matrix of variables X, Y, Z, like this. At X, A, and B be matrices of the same order, such that X equal to E. This is also matrix X, this is matrix, this is also matrix, and all are of same order. Now we can easily apply sequence of elementary column operations or sequence of elementary row operations. Once we do one either row operation, then we will not apply column transformation. We will only apply row transformation unless we get the answer. If we apply row transformation first, we will our series will be row transformation only. If we apply column transformation, then our all the transformations will be only column transformations. We will not apply row transformation. That you have to keep in mind always. In order to apply a sequence of elementary column operations on the matrix equation X equals to AB, we will apply this. order to apply a sequence of elementary operations, okay, need not to write here row or column. We can write elementary operations on the matrix x equation x equal to eb. We apply these row operations simultaneously on x. If we apply row transformation on this matrix we will apply here on RHS, there will be A into B. We will apply on A matrix row operations and here also on X. And if we want to apply column operations, then we will apply on B. Here you can write column, here you can write row. Whenever we are applying row transformation, we will apply in the product, we will apply which is on the left first. And column transformation, we will apply on the right, which is on the second. And simultaneously we will be operating same row operations on this X matrix or column operations on this X matrix. Either whatever we are doing that we will apply on X also, left hand side as well as right hand side, so that equality remains unchanged. Okay, now finding inverse. Inverse, we already know what is inverse. A inverse, if we have a matrix A which is non-singular, determinant of A is not equal to 0. A inverse is nothing but adjoint of A divided by determinant of A. This we already discussed in the previous class. Now finding the inverse without finding adjoint. How will we do that? With the help of elementary row or elementary column transformations. Inverse of matrix using elementary transformation. And try this many times so that you will easily get used to it. Consider the matrix equation. Let's say this is our matrix A, 1 minus 2 3 minus 5, and here 1 0 0 1, and here 1 minus 2 3 minus 5. If you consider this is matrix A, okay, this is matrix I of order 2 cross 2, and this is also, if you see, this is again A. I have written earlier, I was writing x equal to AB. Now instead of x I have written A, then instead of A, instead of this A I have written here I, and instead of B I have written A again. Now when I want to do row transformation, I will place this I on the left side. And when I want to do column transformation, then I will write this A equals to A into I. In this case, I will apply row transformations. In this case, I will apply column transformation. So that on the right hand side, this I is only changed. This I is only changed in RHS, and this A remains unchanged. And I will make this A on the left hand side LHS. This I will make into identity matrix. And let's this is unchanged. This will be some matrix B after elementary transformation, and this will be changed into I. And we know A into B equals to I. That means this is B is A inverse. So B will be, we will be getting A inverse. In this way we will apply. So let's operate here row transformations. First we will try row transformations and try to find its inverse. 1 minus 2, 3 minus 5, and here we will write 1 0 0 1. So we will apply row transformations here. Only row transformation, not column transformation. 3 minus 5. Now if I apply R2 gives R2 minus 3 R. I need here 0 and here 0. To make this identity, what I will do, I will first, and here I need 1 and here 1. Here already I have 1. I will change this, convert into 1, and this into 0, this into 0, and I will operate on both sides, LHS as well as RHS. R2 gives R2, so row 2 will change, row 1 will remain unchanged. R2 gives R2 minus 3 R1. R2 is 3, 3 minus 3, which is 0. Then minus 5 plus 6. So this will become 1. Equals to, first row will remain unchanged. Now, here it is 0 minus 3 times R1. So minus 3. And here 1 minus 3 times 0, which is 1. And this I will not touch. 1 minus 2, 3 minus 4. Why we are applying row transformation? Row transformation in product it will apply on first matrix. Is this clear? Now from this I will apply R1 gives R1 plus 2 R2. Here if I add this 0, how many times? Many times it will still remain 1. So now 1 plus 0, 2 times 0 is 1 only. And this will be R1. R1 is minus 2 plus 5 is 2. So it will become 0 equals to, now this we have to change, minus 3 1, and what will be this entry, 1 R1 plus 2 times R2. So 2 into minus 3 is minus 6 plus 1 minus 5, and this 0 plus 2 times 1. So it will become 2, and here this will remain unchanged. So this matrix we got, this is A, this is B, and this is I. We know A, B equals to I, or BA equals to I. This means A inverse equals to B, or B inverse equals to A. So this matrix is inverse of matrix A. So thus inverse of A is A inverse equals to B. B was minus 5, 2, minus 3. What we can now say, in view of above calculations, we can conclude that if A is a matrix such that A inverse exists, if A is a matrix such that A inverse exists, then to find A inverse using elementary row operations, write A equals to I into A. If we are applying row transformation, row operation, and apply a sequence of row operations on A equal to I till we get I equals to B into A. The matrix B will be the inverse of A. So the obtained matrix B will be the inverse of A matrix.
अरे गांधी ఎందుకు వచ్చారా?
Okay. Now, similarly, if we wish to find A inverse using column operations, we write A equals to A into I and apply secants of column operations on A equals to A into I till we get I equal to AB. And this B will be the inverse of A. Question 1. Let A be such that A into 1, 2, 3, 0, 2, 3, 0, 1, 1 equals to this 0, 0, 1, 1, 0, 0, 0, 1, 0. Then find A inverse. How you will get here A inverse? Which operations you will apply here? We need to make this matrix as identity matrix. But which operations we will apply? Row operations or column operations? Tell me fast. And tell me what is the inverse A inverse. Now it's easy to get A inverse. here this matrix 1, 2, 3, 0, 2, 3, 0, 1, 1 equals to 0, 0, 1, 1, 0, 0, 0, 1, 0. This is A, B, otherwise we can write AX equals to B. And we can write X equals to AB. AB equals
Sir,
to hmm, yes.
sir,
Tell me, do you have any doubts?
show before slide, sir.
Show before fifth,
Before slide, sir.
this one.
1 minute, sir.
Okay, this one.
No, 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 no. Yes, that one.
This one.
Okay, sir, continue. I had taken screenshot.
This.
Okay, continue, sir. Completed. I had taken screenshot.
Okay. So what will we apply here? Tell me faster. Can we apply row transformations here?
No, sir.
Yeah, we will not apply row transformations here because here it was somehow identity first. So it's AI into AI equals to B. So identity is on the right hand side. So we will apply column transformation. And we can write A equals to A into I. It was like this. So we will apply column transformations. So try. This is C1, C2, C3. So we can interchange C1 with C3. Interchange C1 with C3. So here we will also interchange. So this will become A into 3, 3, 1, 2, 2, 1, and this will reach here 1, 0, 0. It is not equality here. And on this side we will get 1, 0, 0, 0, 0, 1, and 0, 1, 0. Now it is still not identity matrix. We will apply C2 goes to C3 and C3 goes to C2. So here I will write A into 3, 3, 1, and now this will change here and this will change here. 1, 0, 0, and 2, 2, 1. 2, 2, 1. On right hand side we will get 1, 0, 0, and this will change here, this will change here. Column 2 with column 3 and column 3 with column 2. So 0, 1, 0, 0, 0, 1. Okay. So we got A into B equals to I. That means this B is A inverse. A inverse equals to B. So B A inverse equals to 312, 302, 10. It's very simple and easy now. Now we have solution of system of linear equations using matrix. Now consider, let's we have two or three or more than three linear equations. Usually we have matrix of order 2 and order 3. So we will be having two linear equations or three linear equations. Maybe in one variable, maybe
Sir,
maybe in two variables, and maybe in three variables. If we have 2 cross 2 matrix, we will be having two linear equations, and we will solve with 2 cross 2 matrix.
sir,
Yes.
Anjali ma'am telling something, sir.
What is actually ma'am saying? We have two class. Which one we sir not
Or someone, sir, hacker.
huh?
Remove, sir, remove.
Okay.
Sir,
Hmm.
Anjali ma'am telling, sir, something. See chart, sir.
Kushi, Kushi, are you there? Can you turn on this camera?
Left, sir.
Hello. If you are comfortable, you can turn on your camera. Otherwise, keep it. It is okay. Bhagya Harshit, what about you?
Continue, sir.
Thank you. No webcam, sir. Okay, fine, fine. I also have problem with webcam because laptop you always after 5 years there will be some problem. Okay, solution of system of linear equation is using matrix. Let's consider three linear equations in three variables: ax a1x plus b1y plus c1z equals to d1. I am using all the variables here a1 a2. Let's say this is a2x plus b2y plus c2z equals to d2, and we have a3x plus b3y plus c3z. This is equal to d3. We have three linear equations in three variables. Our variable is x, y, and z, and a1, b1, c1, d1. These are all constants, or we can say coefficient of x here. This is d1 is coefficient of y, and here c1 is coefficient of z in first linear equation, and d1 is constant term. Now consider let a equals to, we can write this as a1 b1 c1 a2 b2 c2 a3 b3 c, comma. We can write x as a matrix of variables. We have here x, y, and z. and this we can write this constant terms as a separate matrix d1, d2, d3. Here x and b are vectors. X is vector of variables, B is vector of constant terms. Or we can say matrix of order 3 cross 1. This is also 3 cross 1 order matrix. 3 rows, 1 column. This system, these three linear equations and three variables can be represented by the matrix and solved by the matrix in this manner. I will show you how we can solve the given system of equations can be expressed in the form of matrix equation. Ax equals to b. So a1, a2, a3. So we are not using like this. We are using a1, b1, b1, a2, b2, c2, a3, b3, c3. Then x, y, z equals to d1, d2.
Sir,
Hmm.
once explain again.
But isn't it down?
Yes, sir. Please, sir.
Where?
This one before, sir.
Before this.
Yes, sir.
Huh.
Explain, sir. Once.
We have three linear equations in three variables. First equation is this. This is second equation. This is third equation. If we solve them simultaneously, so like we have elimination method, substitution method, cross multiplication method. This matrix method is actually cross multiplication method, but in refined form. So what we will do first, matrix A, if we write it as a form of coefficient matrix. A is coefficient matrix of x, y, and z. First row will be coefficients of x, y, and z of first equation. Second row will be the coefficients of second equation. Coefficients of x variable, y variable, z variable. This is x variable, y variable, z variable. This is equation first. This is equation second. This is equation third. In first row, we will be using the coefficients of first equation. Under x, we will write x coefficient. Under y coefficient, z, coefficient of z. Similarly, in row 2, we will write equation second, coefficients of equation second. So a2, b2, and c2. Similarly, we will write coefficients of x, y, z, a3, b3, c3 in row 3 in matrix A. Then we have this matrix X where we have variable matrix of variables x, y, z, x, y, z, because we have x, y, z in all the three linear equations. Then we have constant terms here on right hand side. We have D1, D2 and D3. So first row we will write D1, second row we will write D2, third row we will write D3. Similarly in X, first X, Y, Z. If we multiply this A into X, you will get same these things. A1, first row, first column. A1X, B1Y, C1Z. You will get first equation and the LHS. And A2X, B2, B2Y, C2Z. You will get second. Then third row, first column, A3X, B3Y, C3Z. You will get third equation on LHS. And we have in between here, we have placed equality. Equality on the right, you will get D1, D2, D3. If you equate, then this will become a matrix having 3 rows and 1 column. This is matrix of 3 cross 3 and this is matrix of 3 cross 1. 3 cross 1. 3 rows, 1 column. So 3 and 3 will get cancelled. So this will be 3 cross 1. Their product. We will get first equation. We know two matrices are equal if their corresponding elements are equal. So we will be getting here A1x, B1y, C1z. That is equal to
Sir,
D1. This system has been converted
result,
into matrix equation. Yes. This system we converted into matrix equation. Now we can easily solve this. Case first. Okay, do you have any doubts? Do you have any doubts? Okay, I will finish this. Case first and case second. Case first.
sir,
Yes. Tell me,
get
तो
back in,
you are only saying, sir.
left, sir, now.
You are leaving.
No, sir, Gandhi came, sir.
Gandhi is there. Is giving you trouble. If A is a non-singular, either a matrix A is singular or non-singular matrix. Non-singular matrix. Then its inverse exists. If a matrix is non-singular, obviously its inverse exists. We can write Ax equal to B. Then we know its inverse exists. We can operate A inverse on both
Sir,
sides. So this is
Stammer
A
came, sir.
inverse B. This is I into X equals to A inverse B. So implies X equals to A inverse.
See
This
chart, sir.
matrix is, huh?
See chart box. Chart.
Chart. This chart. Time up, sir.
Samosa chart.
Entira. Time up, sir. Sir, see. Okay, you want to discontinue from here, class? Otherwise, I will finish this case. Case first.
Sir,
I have
Stammer,
just
sir.
this.
Gandhi came, sir.
Huh?
Prajwal, sir. Stammer.
This matrix equation provides
Sir,
unique
Anjali ma'am
solution
is telling something.
for the given
Sir,
system of equations
sir.
as inverse of the matrices. In this case, system of equations is consistent.
Sir,
Okay. Okay, this class will get over here.
sir, see chat box.
Hey, you guys are playing, huh? Very
Someone
good.
came, sir.
Very good. Very good. So this is not Anjali ma'am, huh?
I don't know, sir. Someone came. Prajwal also came, sir.
Yeah, very good. Okay, see you guys tomorrow.
They Prajwal. ఏంట్రా గాంధీ గడ మాట్లాడు వెళ్ళిపోయింది. अरे भाग्य अंजलि मामा इन लोग भी आगे कर रहा है. अरे भाग्य अंजलि मामा ఎవరు వచ్చారు? రేపు వస్తున్నావా రావట్లేదా?